Hello and welcome to the Cozy Curiosity channel. I'm so glad you found your way here tonight. Maybe the day felt long, or perhaps you're someone who finds peace in pondering the cosmos as sleep draws near. Whatever brought you here, you've arrived at exactly the right place. Tonight, we're embarking on a gentle journey through our home in space, the Milky Way Galaxy. A magnificent spiral of hundreds of billions of stars, swirling through the darkness for over 13 billion years. We'll drift through stellar nurseries where new suns are born, past ancient stars that remember the galaxy's youth, and toward mysteries that astronomers are only beginning to understand. You have nothing to do but rest. Let your breathing slow, your body relax, and your mind wander freely through the vastness of our galactic home. If these peaceful explorations help you unwind or give you a quiet way to end your evening, consider liking and subscribing to the channel. It helps others discover this restful corner of the internet. And let me know in the comments where you are in the world and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, let's begin our journey through the stars. The Milky Way is just one of hundreds of billions of galaxies in the observable universe. When you look up at the night sky and see that hazy band of light stretching from horizon to horizon, you're gazing into the plane of our own galaxy. But our Milky Way, as vast as it is, represents just a tiny fraction of all the galaxies scattered throughout space. Astronomers estimate there are between 200 billion and 2 trillion galaxies in the observable universe, each containing millions, billions, or even trillions of stars. Some galaxies are spirals like ours. Others are elliptical or irregular in shape. Our Milky Way is just one island universe among countless others, separated by vast gulfs of intergalactic space. It's both humbling and comforting to know we're part of something so immense. Our solar system orbits the galactic center at about 828,000 kilometers per hour. You might feel perfectly still right now, resting comfortably as you listen to this. But in reality, you're moving through space at breathtaking speed. Our entire solar system, including Earth, orbits around the center of the Milky Way at roughly 828,000 kilometers per hour, or about 230 kilometers every single second. Despite this incredible velocity, it takes approximately 225 to 250 million years for our solar system to complete just one orbit around the galaxy. This period is sometimes called a cosmic year or galactic year. Since Earth formed about 4.5 billion years ago, we've completed only about 20 trips around the Milky Way. The last time we were at this particular spot in the galaxy, dinosaurs were just beginning their reign on Earth. The Milky Way contains between 100 and 400 billion stars. The exact number of stars in our galaxy remains uncertain, but astronomers estimate there are somewhere between 100 billion and 400 billion suns scattered throughout the Milky Way. This vast range exists because many stars are too faint or too obscured by dust to count directly, especially in the dense regions near the galactic center. Some of these stars are solitary, like our Sun, while many exist in binary or multiple star systems, locked in gravitational dances with companion stars. Each of these hundreds of billions of suns represents a world of nuclear fusion, light, and gravitational influence. Some host their own families of planets, and around those planets might exist conditions suitable for life. The sheer abundance is almost impossible to comprehend. The galaxy's supermassive black hole weighs about 4 million times the mass of our Sun. At the very heart of the Milky Way, Buried deep within a region called Sagittarius A star, lurks a supermassive black hole. This gravitational monster contains about 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. Despite its tremendous mass, this black hole is relatively quiet compared to those in other galaxies. It occasionally flares with X-ray emissions when it consumes nearby gas, or the remnant of an unfortunate star that wandered too close. Radio telescopes can detect the energetic processes occurring around its event horizon, the point of no return beyond which not even light can escape. This cosmic anchor helps hold the inner regions of the galaxy together, a silent heavyweight around which billions of stars orbit. Most of the Milky Way's mass is invisible dark matter. When astronomers calculate the mass of all the visible stars, gas, and dust in the Milky Way, they find something puzzling. The total mass isn't enough to hold the galaxy together, given how fast everything is moving. Stars in the outer regions orbit far too quickly to be held in place by the gravity of visible matter alone. They should fly off into intergalactic space, but they don't. The solution to this mystery is dark matter, an invisible substance that doesn't emit, absorb, or reflect light. Dark matter makes up approximately 85% of the galaxy's total mass, forming a vast halo that extends far beyond the visible disk. We can't see it or directly detect it, but its gravitational effects are unmistakable. Dark matter is the invisible scaffolding that holds our galaxy together. The Milky Way is on a collision course with the Andromeda Galaxy. When you look toward the constellation Andromeda on a dark autumn night, you might just barely make out a faint smudge of light. That smudge is the Andromeda Galaxy, the nearest large spiral galaxy to our own, located about 2.5 million light-years away. Despite the enormous distance, Andromeda and the Milky Way are moving toward each other at about 110 kilometers per second. In approximately 4.5 billion years, these two great spirals will collide. Don't worry though, the collision won't be catastrophic. Stars are so far apart that direct collisions between them are extremely rare. Instead, the two galaxies will pass through each other, their shapes distorting into long tidal tails, before eventually merging into a single, larger elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda. The Milky Way's disk is about 100,000 light-years across. The Milky Way is shaped like a flat disk with a bulge at the center, somewhat like two fried eggs placed back to back. This disk stretches about 100,000 light-years from one edge to the other. To put that distance in perspective, light traveling at 300,000 kilometers per second would take 100,000 years to cross from one side to the other. The disk itself is relatively thin, only about 1,000 light-years thick in most places, though it thickens near the center. Our solar system sits roughly 26,000 to 28,000 light-years from the galactic center, about halfway out from the core to the edge, in a relatively quiet neighborhood between two major spiral arms. There are 4 major spiral arms in the Milky Way. The Milky Way's disk isn't uniform. Instead, it's organized into several spiral arms that wind outward from the central bulge, like the arms of a cosmic pinwheel. Astronomers have identified 4 major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. These arms are regions of higher density, where stars, gas, and dust congregate. They're also where most active star formation occurs, making them brighter and more prominent than the regions between the arms. Our solar system resides in a minor spur called the Orion Spur, or local spur, a smaller branch that lies between the Perseus and Sagittarius arms. It's a relatively calm location, away from the more chaotic star-forming regions of the major arms. The center of the galaxy is obscured by thick clouds of dust. If you look toward the constellation Sagittarius on a summer night, you're gazing toward the center of the Milky Way. But you can't actually see the galactic core in visible light. Dense clouds of interstellar dust, made up of tiny particles of carbon, silicates, and ice, block almost all visible light from the central regions. This dust absorbs and scatters light, creating dark patches and lanes across the Milky Way's band. However, longer wavelengths like infrared and radio waves can penetrate this dust. Using infrared and radio telescopes, astronomers have been able to peer through the obscuration and study the densely packed stars, swirling gas, and supermassive black hole that lie hidden at the galaxy's heart. The Milky Way is estimated to be about 13.6 billion years old. Our galaxy is ancient, nearly as old as the universe itself. The universe began with the Big Bang approximately 13.8 billion years ago. The Milky Way formed relatively soon after, about 13.6 billion years ago, as the first clouds of hydrogen and helium gas began collapsing under gravity. Over billions of years, these early structures merged and grew, eventually forming the spiral galaxy we see today. The oldest stars in the Milky Way, found primarily in the galactic halo and globular clusters, are nearly as old as the galaxy itself, their light carrying information about the early universe. These ancient stars contain very few heavy elements, a clue that they formed from the nearly pure hydrogen and helium present shortly after the Big Bang. Globular clusters are ancient cities of stars orbiting the Milky Way. Scattered around the Milky Way's halo are about 150 known globular clusters, dense spherical collections of stars that can contain anywhere from tens of thousands to over 1 million stars, packed into a relatively small volume. These clusters are among the oldest structures in the galaxy, with ages often exceeding 10 billion years. The stars within them are tightly bound by gravity, creating spectacular spherical swarms that shine like jewels when viewed through a telescope. Globular clusters orbit the galactic center on long elliptical paths that take them high above and below the galactic disk. Studying these clusters helps astronomers understand the early history of the Milky Way and test theories of stellar evolution. The galactic halo extends far beyond the visible disk. Surrounding the flat disk of the Milky Way is a roughly spherical region called the galactic halo. This halo contains old stars, globular clusters, and vast amounts of dark matter. Unlike the disk, which is rich in gas and dust and actively forming new stars, the halo is sparse and mostly devoid of star formation. The stellar halo extends perhaps 100,000 to 200,000 light-years from the galactic center, far beyond the bright disk we normally picture when we think of the Milky Way. Most stars in the halo are ancient and metal-poor, meaning they formed when the galaxy was young and the universe contained few heavy elements. The halo also contains streams of stars, the remnants of smaller galaxies that were torn apart and absorbed by the Milky Way long ago. The Milky Way has absorbed many smaller galaxies over its lifetime. The Milky Way didn't form in isolation. Throughout its history, it has grown by cannibalizing smaller galaxies that wandered too close. These smaller companions were pulled in by the Milky Way's gravity, stretched into long tidal streams. and eventually torn apart. Their stars scattered throughout our galaxy. One of the most significant of these ancient mergers is known as the Gaia Enceladus event, which occurred about 10 billion years ago, when a dwarf galaxy, roughly 1/4 the mass of the Milky Way, merged with ours. This collision added a significant population of stars to the galactic halo and may have helped trigger a period of intense star formation. Even today, the Milky Way continues to consume smaller satellite galaxies, like the Sagittarius dwarf elliptical galaxy. The large and small Magellanic Clouds are satellite galaxies of the Milky Way. If you observe the night sky from the southern hemisphere, you can see two fuzzy patches of light that look like detached pieces of the Milky Way. These are the large Magellanic Cloud and the small Magellanic Cloud, two irregular dwarf galaxies that orbit our own. The large Magellanic Cloud lies about 160,000 light-years away and contains roughly 30 billion stars. The small Magellanic Cloud is a bit farther, about 200,000 light-years distant, and contains around 3 billion stars. These galaxies are visible to the naked eye and have been known to observers in the southern hemisphere for thousands of years. They're gravitationally bound to the Milky Way and are slowly being pulled inward, destined to eventually merge with our galaxy in the distant future. The Milky Way's disk has a slight warp to it. If you could view the Milky Way edge-on from a great distance, you'd notice that the disk isn't perfectly flat. Instead, it has a subtle warp, bending upward on one side and downward on the other, like the brim of a hat that's been slightly bent. This warping is most pronounced in the outer regions of the disk and is thought to be caused by gravitational interactions with satellite galaxies, particularly the Magellanic Clouds. The warp is also influenced by the distribution of dark matter in the galactic halo. This slight deviation from flatness shows that the Milky Way is a dynamic, living structure, constantly being tugged and shaped by the gravitational forces of its cosmic neighbors. Star formation in the Milky Way continues today in giant molecular clouds. The Milky Way is not a static relic of the past. It's an active, living galaxy where new stars are constantly being born. Star formation occurs primarily in giant molecular clouds, vast regions of cold gas and dust that can contain hundreds of thousands to millions of times the mass of the Sun. These clouds are the nurseries where stars come into being. Under the influence of gravity, portions of these clouds collapse, heating up until nuclear fusion ignites in their cores, and a new star is born. The Milky Way forms an estimated 1 to 2 new stars every year. While this might seem like a modest rate compared to some galaxies, over billions of years, it adds up to the hundreds of billions of stars we see today. The Orion Nebula is one of the closest star-forming regions to Earth. If you look at the constellation Orion in the winter sky, you can see a fuzzy patch below the 3 stars of Orion's belt. This is the Orion Nebula, one of the most famous and well-studied star-forming regions in the Milky Way, located about 1/300 light-years away. It's close enough that astronomers can study the process of starbirth in great detail. The nebula glows with the light of young, hot stars that have recently formed from its gas. Hidden within the nebula's dense clouds are even younger stars, still in the process of formation, surrounded by disks of material that may eventually form planets. The Orion Nebula offers a window into how stars, including our own Sun, come into existence. Some stars in the Milky Way are over 13 billion years old. Among the oldest residents of the Milky Way are stars that formed when the galaxy itself was young. These ancient stars, often found in globular clusters or the galactic halo, are more than 13 billion years old, nearly as old as the universe itself. One such star, catalogued as HD WT83 and nicknamed Methuselah, has an estimated age of about 14.5 billion years, which initially seemed impossible, since it would make the star older than the universe. Refined measurements have brought its age down to a more plausible 13.7 billion years, with enough uncertainty to fit within the universe's age. These ancient stars contain almost no heavy elements, a signature of their formation from the nearly pure hydrogen and helium that existed shortly after the Big Bang. The Sun is about halfway through its life in the Milky Way. Our Sun is a middle-aged star, currently about 4.6 billion years old. It formed from a collapsing cloud of gas and dust in the Milky Way's disk, along with the planets, moons, and other objects that make up our solar system. The Sun has enough hydrogen fuel to continue fusing elements in its core for another 5 billion years or so. After that, it will begin to run out of fuel and start to change. It will swell into a red giant, possibly engulfing the inner planets, before eventually shedding its outer layers and leaving behind a dense white dwarf core. So while the Sun is about halfway through its main sequence life, the Milky Way itself will continue spinning through space long after our star fades. Pulsars are rapidly spinning neutron stars created in supernova explosions. Scattered throughout the Milky Way are exotic objects called pulsars, the remnants of massive stars that exploded as supernovae. When a star much more massive than the Sun runs out of fuel, its core collapses catastrophically, triggering an explosion that blasts the outer layers into space. What's left behind is an incredibly dense neutron star, a sphere only about 20 kilometers across, but containing more mass than the Sun. Neutron stars spin incredibly fast, often hundreds of times per second, and emit beams of radiation from their magnetic poles. As these beams sweep past Earth like a lighthouse, we detect regular pulses of radio waves, hence the name pulsar. These cosmic lighthouses are among the most extreme objects in the galaxy. There are likely hundreds of millions of black holes in the Milky Way. Black holes, regions of space where gravity is so strong that not even light can escape, are surprisingly common in the Milky Way. When very massive stars reach the end of their lives and explode as supernova, they can leave behind black holes as remnants. Astronomers estimate there could be anywhere from 10 million to over 100 million stellar mass black holes scattered throughout the galaxy, though most are invisible and undetectable unless they're actively feeding on nearby matter. When a black hole has a companion star, it can pull gas from the star, heating it to millions of degrees and causing it to emit X-rays that we can detect. These X-ray binary systems have revealed the presence of dozens of black holes, but they represent just a tiny fraction of the total. The Milky Way contains vast amounts of gas and dust between the stars. While stars are the most visible component of the Milky Way, the space between them isn't empty. The interstellar medium, as it's called, contains vast clouds of gas, primarily hydrogen, along with tiny grains of dust made of carbon, silicates, and frozen molecules. This material makes up about 10 to 15% of the visible mass of the galactic disk. The gas exists in various forms, from cold molecular clouds where stars form, to warm neutral regions, to hot ionized gas heated by supernova explosions and stellar winds. The dust, though sparse, plays a crucial role by absorbing and scattering starlight and providing surfaces where molecules can form, ultimately contributing to the chemistry that makes planets and life possible. Supernovae enrich the Milky Way with heavy elements. When massive stars explode as supernovae, they don't just create spectacular displays of light and energy. These explosions are the universe's primary factories for creating heavy elements. Inside a star's core, nuclear fusion creates elements up to iron, but elements heavier than iron, like gold, silver, and uranium, are primarily produced during the intense conditions of a supernova explosion. These newly forged elements are blasted into space, mixing with the interstellar medium. Over time, this enriched material collapses to form new generations of stars and planets. Every atom of iron in your blood, every atom of calcium in your bones, was created in the heart of a massive star and scattered across the galaxy in a supernova billions of years ago. Stellar winds and supernova explosions create bubbles in the interstellar medium. The space between stars isn't uniform or static. Hot, massive stars emit powerful stellar wind, streams of charged particles that blow outward at high speeds. When these stars explode as supernova, the energy and expanding debris create shock waves that sweep through the surrounding gas. These processes carve out large, low-density regions called superbubbles, which can span hundreds of light years. The gas inside these bubbles is hot and thin, heated to millions of degrees by the violence of stellar death. Our solar system actually resides within one such structure, called the local bubble, a cavity about 300 light-years across that was likely created by multiple supernovae over the past 10 to 20 million years. The Milky Way's magnetic field threads through the entire galaxy. Like Earth, the Milky Way has a magnetic field, though it's far weaker and more complex. This galactic magnetic field is generated by the motion of charged particles in the galaxy's gas and permeates the entire structure, threading through the spiral arms, the disk, and even the halo. The field influences the behavior of cosmic rays, charged particles moving at nearly the speed of light, guiding them along field lines and affecting how they propagate through the galaxy. It also plays a role in star formation, helping to regulate how gas clouds collapse. Astronomers study the galactic magnetic field by observing how it affects the polarization of starlight and the emission from interstellar dust. Cosmic rays are high-energy particles that constantly bombard the Milky Way. Cosmic rays are not actually rays at all, but rather high-energy particles, mostly protons, that zip through the galaxy at nearly the speed of light. These particles originate from various sources, including supernova explosions, pulsars, and possibly even the supermassive black hole at the galaxy's center. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that rain down on the surface. While Earth's magnetic field and atmosphere protect us from most of this radiation, cosmic rays pose a challenge for astronauts in space and for electronics on satellites. Studying cosmic rays helps astronomers understand the most violent processes in the galaxy. The galactic center glows brightly in infrared and radio wavelengths. While visible light from the galactic center is blocked by dust, the core of the Milky Way shines brilliantly at longer wavelengths. Infrared telescopes can peer through the dust and reveal millions of stars packed densely around the central black hole. The core region, known as the central molecular zone, is a chaotic environment filled with hot gas, dense molecular clouds, and intense star formation. Radio observations reveal even more, including the supermassive black hole itself, Sagittarius A star, which occasionally flares as it consumes nearby material. The galactic center is one of the most energetic and dynamic regions in the entire Milky Way, a place where gravity, magnetism, and stellar evolution create a cosmic maelstrom. The Milky Way rotates differentially, meaning the inner regions orbit faster than the outer regions. Unlike a solid object that rotates as one piece, the Milky Way doesn't spin uniformly. Instead, it exhibits differential rotation. The inner parts of the galaxy orbit the center more quickly than the outer parts. This is similar to how the inner planets in our solar system orbit the Sun faster than the outer planets. However, things get interesting in the outer disk. Instead of continuing to slow down as expected, the rotation speed flattens out, remaining roughly constant, far from the center. This flat rotation curve is one of the key pieces of evidence for dark matter. Without the extra gravitational pull of an invisible mass halo, the outer stars should be moving much slower, but they're not. Open star clusters are groups of young stars born together. As you gaze at the Milky Way, you might notice small groupings of stars that appear to travel together. These are open star clusters, loose collections of stars that formed from the same giant molecular cloud and remain gravitationally bound, at least for a while. Open clusters typically contain anywhere from a few dozen to a few thousand stars and are found in the disk of the galaxy, where star formation is active. The Pleiades, also known as the Seven Sisters, is one of the most famous open clusters, visible to the naked eye as a small dipper-shaped group of stars. Unlike globular clusters, which are ancient and tightly packed, open clusters are relatively young, often just a few million to a few 100 million years old, and will eventually disperse as their stars drift apart. Red giants are elderly stars nearing the end of their lives. As stars like our Sun age and begin to exhaust the hydrogen fuel in their cores, they undergo dramatic changes. The core contracts and heats up, causing the outer layers to expand enormously. The star swells into a red giant, becoming hundreds of times larger than it was during its main sequence phase. Despite this expansion, the surface cools, giving the star a reddish hue. Red giants are some of the brightest stars in the Milky Way because of their enormous size. Eventually, these stars will shed their outer layers in a gentle stellar wind or a more dramatic planetary nebula, leaving behind a dense white dwarf core. The Milky Way contains countless red giants at various stages of this transformation. White dwarfs are the dense remnants of Sun-like stars. When stars like our Sun exhaust their nuclear fuel and shed their outer layers, what remains is a white dwarf, an incredibly dense object about the size of Earth, but containing roughly the mass of the Sun. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs no longer undergo fusion. Instead, they slowly cool and fade over billions of years, radiating away their residual heat. These stellar remnants are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect. The Milky Way contains billions of white dwarfs, the quiet end states of the vast majority of stars in the galaxy, including the eventual fate of our own Sun. Planetary nebulae are the beautiful death shrouds of Sun-like stars. Despite their name, Planetary nebulae have nothing to do with planets. They're glowing shells of gas ejected by dying stars. When a sun-like star becomes a red giant and begins to lose its outer layers, it creates an expanding shell of gas that glows when illuminated by the hot, exposed core of the star at the center. These nebulae come in a stunning variety of shapes, from spheres to rings to intricate butterfly patterns shaped by magnetic fields, stellar rotation, and companion stars. Planetary nebulae are relatively short-lived, lasting only about 10,000 to 50,000 years before the gas disperses into the interstellar medium. They return chemically enriched material to the galaxy, contributing to the cycle of stellar birth and death. The galaxy contains mysterious fast radio bursts detected from distant sources. In recent years, astronomers have detected brief, intense pulses of radio waves coming from deep space, phenomena known as fast radio bursts, or FRBs. These bursts last only milliseconds, but release as much energy as the sun emits in several days. Most FRBs appear to originate from distant galaxies, billions of light years away, though a few have been detected within or near the Milky Way. The exact cause of FRBs remains a mystery, though leading theories involve highly magnetized neutron stars called magnetars. These enigmatic signals have opened up a new area of astrophysics, and as more are detected and studied, they may reveal secrets about the universe's most extreme environment. Hypervelocity stars are racing out of the Milky Way at incredible speeds. Most stars orbit peacefully within the Milky Way, but a small population of stars, known as hypervelocity stars, are moving so fast that they will eventually escape the galaxy entirely. These stars can reach speeds of over 1,000 kilometers per second, more than twice the escape velocity needed to leave the Milky Way. Most hypervelocity stars are thought to have been accelerated by gravitational interactions with the supermassive black hole at the galactic center. In a close encounter, a binary star system can be disrupted, with one star captured by the black hole and the other flung outward at tremendous speed. These stellar exiles offer clues about the violent dynamics near the galaxy's core. The Milky Way's stellar population is divided into population 1 and population 2 stars. Astronomers classify stars into different populations based on their age and chemical composition. Population I stars are relatively young, metal-rich stars found primarily in the disk of the galaxy. They formed from gas clouds that had been enriched with heavy elements from previous generations of stars. Our Sun is a population 1 star. Population 2 stars, on the other hand, are older, metal-poor stars found mainly in the galactic halo and in globular clusters. They formed early in the galaxy's history, when there were fewer heavy elements available. There's also a hypothetical population 3, the very first stars that formed from pure hydrogen and helium, shortly after the Big Bang, though none have been directly observed. Binary star systems are incredibly common in the Milky Way. If you imagine stars as solitary objects like our Sun, you'd be surprised to learn that most stars actually have companions. Astronomers estimate that more than half of all stars in the Milky Way exist in binary or multiple star systems, gravitationally bound to one or more partner stars. In these systems, 2 or more stars orbit around a common center of mass, held together by their mutual gravitational attraction. Some binaries are so close that they orbit each other in a matter of hours, while others are separated by thousands of astronomical units and take thousands of years to complete one orbit. Binary systems play crucial roles in our understanding of stellar masses, evolution, and exotic phenomena like X-ray binaries and type E or ER supernovae. Cepheid variable stars helped measure the size of the Milky Way. In the early 20th century, astronomers didn't know the true size of the Milky Way, or even whether other galaxies existed. That changed thanks to a special class of stars called Cepheid variables. These are pulsating stars whose brightness varies regularly over periods of days to months. The American astronomer Henrietta Leavitt discovered that there's a relationship between a Cepheid's pulsation period and its intrinsic brightness. By measuring a Cepheid's period, astronomers could determine how bright it truly is, and by comparing that to how bright it appears, they could calculate its distance. This discovery allowed astronomers to measure distances to far-off star clusters and other galaxies, revolutionizing our understanding of the scale of the universe. The Milky Way is part of a larger structure called the local group. The Milky Way doesn't float alone in space. It's part of a collection of more than 50 galaxies known as the local group, a gravitationally bound cluster that spans about 10 million light-years. The two largest members are the Milky Way and the Andromeda Galaxy, with a third, smaller spiral, the Triangulum Galaxy, rounding out the major galaxies. The rest are dwarf galaxies, small irregular or elliptical collections of stars that orbit the larger galaxies. The local group itself is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies. And beyond that, the universe is organized into vast filaments and sheets of galaxies separated by enormous voids. The Great Rift is a series of dark dust clouds that splits the Milky Way. When you observe the Milky Way on a clear, dark night, you might notice dark lanes running through the bright band of stars, giving it a divided appearance. This feature, called the Great Rift or Dark Rift, isn't a region devoid of stars. Instead, it's caused by thick clouds of interstellar dust that block the light from stars behind them. These dark nebulae, including famous regions like the Coalsack Nebula, are actually dense, cold clouds where star formation may eventually occur. The Great Rift is most prominent when looking toward the galactic center, where the dust clouds are thickest. It's a reminder that the Milky Way is not just stars, but a complex tapestry of light and shadow. The Milky Way has a bar-shaped structure at its center. For many years, astronomers debated whether the Milky Way was a simple spiral galaxy or a barred spiral, where a central bar-shaped structure extends from the core before the spiral arms begin. Thanks to infrared observations that can see through the dust, we now know that the Milky Way is indeed a barred spiral. The central bar is made up of stars and gas and measures about 27,000 light-years from end to end. It rotates more slowly than the surrounding disk and plays a role in funneling gas toward the galactic center, potentially feeding star formation and the central black hole. This bar gives our galaxy a slightly different structure than originally imagined, adding complexity to our home in space. Stars in the Milky Way have a wide range of masses, from tiny to monstrous. Not all stars are created equal. The smallest stars, called red dwarfs, contain as little as 8% of the sun's mass. These faint, cool stars burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. On the other end of the spectrum are the massive blue giants, stars with tens or even hundreds of times the sun's mass. These behemoths burn hot and bright, but live fast and die young, exhausting their fuel in just a few million years before exploding as supernovae. The mass of a star determines almost everything about it, from its temperature and color to its lifespan and ultimate fate. Red dwarfs are the most common type of star in the Milky Way. If you were to count all the stars in the Milky Way by type, the vast majority would be red dwarfs. Small, cool, faint stars that make up about 70% of all stars in the galaxy. Despite their abundance, red dwarfs are so dim that not a single one is visible to the naked eye from Earth. The nearest star to our solar system, Proxima Centauri, is a red dwarf located just over 4 light-years away. These stars are incredibly long-lived because they fuse their hydrogen fuel slowly and efficiently. Some red dwarfs formed shortly after the galaxy's birth are still shining today and will continue to do so for trillions of years, long after more massive stars have exhausted their fuel. The Milky Way's spiral structure may be maintained by density waves. The spiral arms of the Milky Way aren't solid structures that rotate like the blades of a fan. Instead, they're regions of higher density that stars, gas, and dust pass through as they orbit the galaxy. This concept, known as density wave theory, suggests that the spiral pattern is a wave that propagates through the disk, compressing gas and triggering star formation as it goes. Stars spend part of their orbits within the arms and part of their orbits between them. The arms appear brighter because they contain more gas, dust, and young, luminous stars. This dynamic picture explains why spiral arms can persist for billions of years without winding up completely. The Sun may have formed in a now dispersed star cluster. Our Sun likely didn't form alone. Most stars are born in clusters, from the collapse of large molecular clouds that fragment into many individual stars. The Sun probably formed 4.6 billion years ago in a cluster containing hundreds or thousands of stars. Over time, gravitational interactions and the influence of the galaxy's rotation would have dispersed this cluster, scattering its member stars across the Milky Way. Today, the Sun's siblings, stars that formed from the same cloud at the same time, are scattered throughout the galaxy, and we have no easy way to identify them. Recent efforts using chemical abundances and stellar ages have tentatively identified a few possible solar siblings, but most have been lost to time. Rogue planets drift through the Milky Way without orbiting a star. Not all planets are tethered to stars. Some worlds, called rogue planets or free-floating planets, wander through the galaxy untethered, drifting through the darkness of interstellar space. These planets may have formed around stars and been ejected through gravitational interactions with other planets or passing stars, or they may have formed independently from collapsing gas clouds. Estimating the number of rogue planets is difficult, but some studies suggest there could be billions or even trillions of them in the Milky Way, possibly outnumbering stars. These lonely worlds are cold, dark, and incredibly difficult to detect, though advances in infrared astronomy are beginning to reveal them. The Milky Way has satellite dwarf galaxies beyond the Magellanic Clouds. In addition to the large and small Magellanic Clouds, the Milky Way has more than 50 known satellite galaxies, small dwarf galaxies that orbit our own. Most of these satellites are extremely faint and contain only a few thousand to a few million stars. They've been discovered in recent years thanks to large-scale sky surveys that can detect faint, diffuse objects. Some, like the Sagittarius Dwarf Elliptical Galaxy, are being actively torn apart by the Milky Way's gravity, their stars forming long streams that wrap around our galaxy. These satellites provide valuable information about how galaxies grow and evolve, as well as clues about the nature of dark matter. The cosmic recycling process turns old stars into new ones. The Milky Way is not a static museum of stars. It's a dynamic system where matter is constantly recycled. Stars form from clouds of gas and dust, fuse lighter elements into heavier ones throughout their lifetimes, and then return enriched material to the interstellar medium when they die, either through gentle stellar winds or violent supernova explosions. This enriched gas mixes with the surrounding material and eventually collapses to form new stars and planets. Each generation of stars is slightly richer in heavy elements than the last, a process known as chemical evolution. The Sun and our solar system are products of this cosmic recycling, built from the remnants of countless earlier generations of stars. Stellar collisions are rare, but can occur in dense regions. In the vast emptiness of space, stars are spread so far apart that direct collisions are extraordinarily rare. However, in the densest regions of the galaxy, such as the cores of globular clusters or near the supermassive black hole at the galactic center, stars are packed closely enough that collisions become possible. When two stars collide, the result depends on their masses and speeds. In some cases, they may merge to form a single, more massive star, potentially triggering unusual stellar evolution paths. In other cases, the collision may be more disruptive, scattering material into space. These rare events offer astronomers glimpses of extreme stellar interactions. The Milky Way's rotation has created a flat, disc-like structure. The Milky Way's distinctive flat, disc-like shape is a direct result of its rotation. When the galaxy first formed, it was a roughly spherical cloud of gas and dark matter. As this cloud collapsed under gravity, it began to spin, and the rotation caused it to flatten into a disk. Material that wasn't moving in the plane of rotation would collide with other material, losing energy and settling into the disk. This process is similar to how a lump of dough flattens when you spin it to make pizza. The rotation also explains why most stars, gas and dust in the galaxy, orbit in roughly the same direction. The halo and globular clusters, which formed before the disk fully settled, retain their more spherical distribution. Tidal streams mark the remains of consumed galaxies. As the Milky Way has absorbed smaller galaxies over billions of years, it has left behind subtle traces in the form of tidal streams. These are long, thin ribbons of stars that wrap around the galaxy, stretching across hundreds of thousands of light years. They're created when the gravity of the Milky Way pulls a smaller galaxy apart, stretching it into a stream along its orbit. The Sagittarius stream, for example, wraps around the Milky Way multiple times and marks the slow destruction of the Sagittarius dwarf elliptical galaxy. By studying these streams, astronomers can reconstruct the history of past galactic mergers and better understand how the Milky Way grew to its current size. The galactic habitable zone is the region where life may be most likely to arise, while the Milky Way contains hundreds of billions of stars. Not all locations in the galaxy are equally hospitable to life. The concept of the galactic habitable zone suggests that life is most likely to arise in a middle region of the disk, not too close to the galactic center, and not too far out in the outer reaches. Too close to the center, frequent supernovae, intense radiation, and gravitational disturbances might sterilize planets. Too far out, there may not be enough heavy elements to form rocky planets. Our solar system sits comfortably within this habitable zone, about halfway between the center and the edge, in a relatively calm, stable region, with enough heavy elements to build planets and potentially support life. Some stars are slung out of the galaxy entirely. Beyond hypervelocity stars, which are fast enough to escape the galaxy, there are stars that have already done so. These intergalactic stars were ejected through gravitational interactions, sometimes with the central black hole or during galaxy mergers. Astronomers have detected individual stars and even star clusters floating in the space between galaxies within the local group. These lonely exiles travel through the cold darkness of intergalactic space, no longer bound to any galaxy. Their existence shows that the boundaries between galaxies are not as sharp as we might think, and that the space between galaxies is not entirely empty. The Fermi bubbles are enormous structures extending above and below the galactic center. In 2010, the Fermi Gamma Ray Space Telescope discovered two enormous bubbles of high-energy gamma rays extending 25,000 light-years above and below the center of the Milky Way. These structures, now called the Fermi bubbles, are thought to be the result of a massive burst of energy from the supermassive black hole at the galaxy's core, possibly triggered by it consuming a large amount of matter in the relatively recent past, perhaps just a few million years ago. These bubbles also emit X-rays and radio waves, suggesting they're filled with energetic particles and magnetic fields. Their discovery reveals that the galactic center, though quiet now, was far more active in the recent past. The Milky Way is moving through space toward the Great Attractor. The Milky Way isn't stationary in the universe. Along with the rest of the local group, it's being pulled through space at about 600 kilometers per second toward a region in the constellation Centaurus. This mysterious destination is known as the Great Attractor, a massive concentration of mass that exerts a powerful gravitational influence on nearby galaxies. However, the Great Attractor itself appears to be just part of a much larger structure called the Laniakea supercluster, a vast assembly of galaxies, including the Milky Way, spanning over 500 million light-years. We're all flowing like rivers through space toward this immense cosmic structure. Dark nebulae block starlight and hide star-forming regions. Dark nebulae are cold, dense clouds of gas and dust that block the light from stars behind them, appearing as dark patches against the bright background of the Milky Way. These clouds are some of the coldest places in the galaxy, with temperatures just a few degrees above absolute zero. Despite their appearance, dark nebulae are not empty voids. They're the future nurseries where stars will eventually form. Some of the most famous dark nebulae include the Horsehead Nebula and the Coalsack Nebula. By studying these clouds with infrared and radio telescopes, which can see through the dust, astronomers can watch the earliest stages of star formation unfold. The Milky Way will eventually exhaust its gas and cease forming new stars. The Milky Way is still forming new stars, but it won't be able to do so forever. The galaxy has a finite supply of gas, and as more and more of it is converted into stars or ejected through galactic winds, the rate of star formation will decline. Astronomers estimate that at the current rate, the Milky Way has enough gas to continue forming stars for several billion more years. Eventually, though, the gas will run out, and the galaxy will become a quieter place, populated mostly by old fading stars, white dwarfs, neutron stars, and black holes. This distant future won't arrive for many billions of years, long after the sun itself has died. Exoplanets are common throughout the Milky Way. For centuries, we knew of only one planetary system. Dark nebulae block starlight and hide star-forming regions. Dark nebulae are cold, dense clouds of gas and dust that block the light from stars behind them, appearing as dark patches against the bright background of the Milky Way. These clouds are some of the coldest places in the galaxy, with temperatures just a few degrees above absolute zero. Despite their appearance, dark nebulae are not empty voids. They're the future nurseries where stars will eventually form. Some of the most famous dark nebulae include the Horsehead Nebula and the Coalsack Nebula. By studying these clouds with infrared and radio telescopes, which can see through the dust, astronomers can watch the earliest stages of star formation unfold. The Milky Way will eventually exhaust its gas and cease forming new stars. The Milky Way is still forming new stars, but it won't be able to do so forever. The galaxy has a finite supply of gas, and as more and more of it is converted into stars or ejected through galactic winds, the rate of star formation will decline. Astronomers estimate that at the current rate, the Milky Way has enough gas to continue forming stars for several billion more years. Eventually, though, the gas will run out, and the galaxy will become a quieter place, populated mostly by old, fading stars, white dwarfs, neutron stars, and black holes. This distant future won't arrive for many billions of years, long after the sun itself has died. Exoplanets are common throughout the Milky Way. For centuries, we knew of only one planetary system in the galaxy, our own. That changed in the 1990s with the discovery of the first exoplanets, planets orbiting stars other than the sun. Since then, thanks to missions like Kepler and TESS, astronomers have discovered thousands of exoplanets, with many more candidates awaiting confirmation. These planets come in an astonishing variety, from scorching hot Jupiters, orbiting close to their stars, to rocky super-Earths, to frigid ice giants. Statistical studies suggest that nearly every star in the Milky Way hosts at least one planet, meaning there could be hundreds of billions of planets in the galaxy, offering countless opportunities for diverse worlds and possibly life. Some exoplanets may orbit in the habitable zone, where liquid water could exist. Among the thousands of discovered exoplanets, some orbit their stars at just the right distance to maintain liquid water on their surfaces, a condition considered essential for life as we know it. This region around a star is called the habitable zone, or Goldilocks zone. Planets in this zone are not too hot and not too cold, allowing water to exist as a liquid rather than as ice or vapor. Earth sits within the Sun's habitable zone, and astronomers have now identified dozens of exoplanets in similar locations around other stars. While being in the habitable zone doesn't guarantee a planet has life, it increases the chances that conditions might be right. The search for extraterrestrial intelligence focuses on signals from the Milky Way. For decades, scientists have been searching for signs of intelligent life beyond Earth by listening for radio signals that might be transmitted by advanced civilizations elsewhere in the Milky Way. This effort, known as the Search for Extraterrestrial Intelligence, or SETI, uses large radio telescopes to scan the skies for unusual patterns or narrow-band signals that would stand out from natural cosmic noise. So far, no confirmed signals have been detected, but the search continues. With hundreds of billions of stars in the galaxy, And the recent discovery that planets are common, the possibility that we're not alone, has never seemed more plausible. The question remains whether life, especially intelligent life, is common or rare. The Milky Way's future is tied to the eventual collision with Andromeda. About 4.5 billion years from now, the Milky Way and Andromeda will collide in a slow gravitational ballet that will last for billions of years. During the first pass, the two galaxies will distort each other, creating spectacular tidal tails of stars and gas stretching across space. They'll swing past one another, then gravity will pull them back together for a second pass, and then a third. Eventually, they'll merge into a single, giant, elliptical galaxy. This new galaxy, sometimes whimsically called Milkomeda, will no longer have the beautiful spiral structure we know. Instead, it will be a more chaotic, loosely organized collection of stars. The good news is that individual stars are so far apart that actual collisions will be rare. Our Sun, if it still exists as a star at that point, will likely survive the merger, though it may end up in a very different part of the new galaxy. The Milky Way reminds us of our place in the universe. Throughout this journey, we've drifted through spiral arms and stellar graveyards, past ancient stars and newborn suns, toward the galactic center and out to the lonely halo. The Milky Way is vast, containing hundreds of billions of stars, planets, and worlds we can barely imagine. It's ancient, with a history stretching back over 13 billion years. And it's dynamic, constantly changing, forming new stars, absorbing smaller galaxies, and slowly marching toward an eventual merger with Andromeda. Yet for all its grandeur, the Milky Way is just one galaxy among billions in the universe. It's humbling to realize our place within this cosmic tapestry, and yet also comforting to know we're part of something so magnificent and enduring. The Milky Way contains neutron stars with incredible properties. Neutron stars are among the strangest objects in the galaxy. When a massive star explodes as a supernova, it can leave behind a core so dense that protons and electrons are crushed together to form neutrons. The result is a neutron star, typically only about 20 kilometers across, but containing more mass than the Sun. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects have the strongest magnetic fields in the universe, and their surfaces are scorching hot, reaching millions of degrees. Some neutron stars spin hundreds of times per second, and their extreme properties make them natural laboratories for testing the laws of physics under conditions we can never recreate on Earth. Novae are smaller stellar explosions that can repeat. While supernovae destroy their host stars, novae are less violent eruptions that allow the star to survive and potentially explode again. A nova occurs when a white dwarf in a binary system accumulates hydrogen from its companion star. This hydrogen builds up on the white dwarf's surface until it reaches a critical temperature and pressure, triggering a runaway nuclear fusion reaction. The explosion blasts the accumulated material into space, causing the star to temporarily brighten by thousands or even tens of thousands of times. Unlike a supernova, the white dwarf survives this event and can accumulate more material to produce another nova decades or centuries later. These recurrent novae show us that stellar death can come in stages. The Milky Way's oldest stars contain almost no heavy elements. When the first stars formed in the early universe, they were made almost entirely of hydrogen and helium, the only elements created in the Big Bang. These ancient stars fused lighter elements into heavier ones, and when they died, scattered those heavier elements into space. The oldest stars still surviving in the Milky Way formed from gas that had been only slightly enriched by this first generation. As a result, they contain almost no heavy elements, a property astronomers call low metallicity. By studying these metal-poor stars, primarily found in the galactic, halo and in globular clusters, astronomers can learn about the early chemical evolution of the galaxy and glimpse conditions in the universe's youth. Star clusters can be disrupted by the galaxy's tidal forces. Open star clusters, those loose collections of young stars born together, don't last forever. As they orbit through the Milky Way, they experience tidal forces from the galaxy's gravitational field. Stars on the outer edges of the cluster can be stripped away, gradually dispersing the cluster over hundreds of millions of years. Additionally, close encounters with giant molecular clouds or other massive objects can further disrupt the cluster. Most open clusters completely dissolve within 1 billion years or so, their member stars scattered throughout the galaxy. In contrast, the more tightly bound globular clusters can survive for many billions of years, though even they slowly lose stars over time through a process called evaporation. The galactic fountain model describes gas circulation in the Milky Way. Gas in the Milky Way doesn't just stay put. Hot gas, heated by supernova explosions and stellar winds, can be blown upward out of the galactic disk, rising hundreds or even thousands of light years above the plane. As this gas cools, it eventually falls back down toward the disk, creating a circulation pattern known as the galactic fountain. This cycling of material helps regulate star formation and distributes heavy elements throughout the galaxy. The fountain also connects the disk to the halo, allowing material to flow between these regions. It's one of the processes that makes the galaxy a dynamic, interconnected system rather than a collection of isolated parts. Wolf-Rayet stars are massive stars shedding their outer layers. Among the most massive and luminous stars in the Milky Way are Wolf-Rayet stars, hot giants that have lost their outer hydrogen envelopes through powerful stellar winds. These stars are in the late stages of their evolution, having already burned through their hydrogen and helium. They shine with surface temperatures exceeding 30,000 degrees Celsius and lose mass at prodigious rates, blowing off material equivalent to Earth's mass every few thousand years. The strong winds from Wolf-Rayet stars enrich the surrounding space with heavy elements and can trigger the formation of new stars in nearby clouds. These massive stars are destined to end their lives as supernovae, possibly leaving behind neutron stars or black holes. Blue stragglers are mysteriously young stars in old clusters. When astronomers study ancient globular clusters, they expect to find only old, evolved stars, since all the cluster members formed at roughly the same time billions of years ago. However, they've discovered a population of stars called blue stragglers that appear young, hot, and blue, as if they're still on the main sequence. This seems impossible in such old clusters. The leading explanation is that blue stragglers form through stellar mergers or mass transfer in binary systems. When two stars collide, or when one star strips material from another, the result can be a star with more mass and a rejuvenated appearance, giving it the characteristics of a younger star, despite its ancient origins. The Milky Way's interstellar medium contains complex organic molecules. The space between stars isn't just hydrogen and helium. Over the decades, radio astronomers have detected more than 200 different molecules in interstellar clouds, including many complex organic compounds. These include molecules like formaldehyde, methanol, ethanol, amino acids, and even sugar molecules. Some of these compounds are the building blocks of life as we know it. They form on the surfaces of dust grains in cold molecular clouds through chemical reactions driven by ultraviolet light and cosmic rays. The presence of these organic molecules in space suggests that the ingredients for life are common throughout the galaxy, and they may have been delivered to the early Earth by comets and asteroids. Herbig-Haro objects reveal newborn stars hidden in clouds. When stars are in the process of forming, they're often hidden deep within dense clouds of gas and dust, but their presence can be revealed by spectacular features called Herbig-Haro objects. These are bright patches of nebulosity created when jets of gas, blasted out from the poles of a young star at hundreds of kilometers per second, slam into the surrounding cloud. The collisions heat the gas to thousands of degrees, making it glow. Herbig-Haro objects can extend for several light years from their parent stars and change noticeably over just a few years, which is remarkably fast in astronomical terms. They provide visible evidence of the violent processes accompanying starbirth. Some stars have been flung from the galactic disk into the halo. Most stars in the Milky Way follow relatively orderly orbits within the disk, but some have been accelerated to such high velocities that their orbits take them far out into the galactic halo. These high-velocity stars aren't moving fast enough to escape the galaxy entirely, but their paths are highly elliptical, carrying them thousands of light years above and below the disk before plunging back down. Many of these stars are thought to be old disk stars that received a gravitational kick from a passing massive object, or from the spiral density wave. Studying their unusual orbits helps astronomers understand the distribution of mass in the galaxy and the frequency of violent dynamical events. The Milky Way is surrounded by a corona of hot gas. Beyond the visible disk and halo, the Milky Way is enveloped in an even larger, extremely hot corona of gas, extending hundreds of thousands of light years from the galactic center. This gas, heated to temperatures of millions of degrees, is so tenuous that it's nearly invisible, but it contains significant amounts of mass. The corona is thought to be a reservoir of gas that will eventually cool and fall onto the disk, fueling future star formation. It may also contain a significant fraction of the galaxy's missing baryonic matter, the ordinary matter that should exist based on cosmological models, but hasn't been fully accounted for in the visible structures. Massive stars create bubbles in space during their lifetimes. Long before they explode as supernovae, massive stars reshape their surroundings. These stars emit powerful stellar winds and intense radiation that push away nearby gas, creating expanding bubbles of hot, low-density material. Multiple massive stars in a star-forming region can collectively create enormous superbubbles that can be hundreds of light years across. These bubbles can persist for millions of years, and when the massive stars eventually explode as supernovae, they inject even more energy into these structures. The expanding shells of superbubbles can compress surrounding gas, potentially triggering new waves of star formation at their edges, demonstrating how generations of stars influence each other. The Milky Way's rotation curve remains flat at large distances. When astronomers measure how fast objects orbit the Milky Way at different distances from the center, they create what's called a rotation curve. Based on the visible matter in the galaxy, the rotation speed should decrease as you move outward from the center, similar to how planets farther from the Sun orbit more slowly. However, observations show that the rotation curve remains flat, meaning that stars and gas in the outer regions orbit just as fast as those closer in. This unexpected behavior is one of the strongest pieces of evidence for dark matter. The flat rotation curve suggests the galaxy is embedded in a massive halo of invisible matter, whose gravity keeps the outer regions moving faster than they otherwise would. Stellar streams trace ancient merger events. Wrapped around the Milky Way, like ghostly ribbons, are stellar streams. Long, narrow structures made up of stars from smaller galaxies or star clusters that have been torn apart by tidal forces. The Sagittarius stream is one of the most prominent, looping around the galaxy multiple times as it slowly unravels. These streams are incredibly useful for mapping the gravitational field of the Milky Way and for understanding the history of galactic mergers. Each stream tells a story of cosmic violence, marking the final chapter in the life of a smaller galaxy or cluster that ventured too close to the Milky Way's gravitational grip. The Milky Way has experienced multiple starburst epochs. Throughout its history, the Milky Way has experienced periods of intense star formation called starburst episodes. These bursts were often triggered by major merger events, when the collision with another galaxy compressed large amounts of gas, leading to a sudden surge in the birth of new stars. Evidence from stellar ages and chemical compositions suggests that the Milky Way has undergone several such episodes, with stars forming at rates 10 or even 100 times higher than today's rate. Between these bursts, star formation would slow down until new gas accumulated or another merger occurred. This episodic pattern of activity is common among galaxies throughout the universe. Stellar archaeology studies the oldest stars to learn about galactic history, just as archaeologists study ancient artifacts to learn about human history. Stellar archaeologists study the oldest stars in the Milky Way to uncover its past. These ancient stars, with their low metallicities and unusual orbits, are relics from the galaxy's earliest days. By analyzing their composition, motions and distributions, astronomers can reconstruct what conditions were like when the Milky Way was young, how it assembled from smaller structures, and what the earliest generations of stars were like. Some of these ancient stars may even contain elements created by the very first stars in the universe, providing a direct link to cosmic dawn. The Milky Way contains thousands of supernova remnants. Every supernova leaves behind an expanding shell of gas and debris that glows with X-rays and radio waves for thousands, or even tens of thousands of years. These supernova remnants can be seen scattered throughout the galactic disk, though most are faint and require sensitive instruments to detect. Some, like the Crab Nebula, are famous objects easily visible through telescopes. Supernova remnants play important roles in the galaxy's ecology, heating the interstellar medium, creating cosmic rays, and dispersing heavy elements. They're also beautiful, with intricate filamentary structures shaped by magnetic fields and shock waves. Over time, these remnants fade and merge into the surrounding interstellar medium. Runaway stars are fleeing from their birthplaces at high speeds. Occasionally, a star receives a sudden gravitational kick that sends it racing through the galaxy, at speeds much higher than its neighbors. These runaway stars can be created when a binary companion explodes as a supernova, releasing the surviving star from their gravitational bond and flinging it outward. Alternatively, close encounters between stars in dense clusters can eject one or more stars at high velocities. Runaway stars often leave behind bow shocks, curved structures of compressed gas similar to the wake of a boat that form as the star plows through the interstellar medium faster than the local sound speed. These bow shocks make runaway stars easier to identify. The galactic center hosts a dense cluster of young, massive stars. Surprisingly, the region immediately surrounding the Milky Way's supermassive black hole contains a cluster of young, massive stars. This is puzzling because the strong tidal forces near the black hole should prevent star formation from occurring there. Somehow, these stars managed to form within the last few million years, despite the hostile environment. One possibility is that they formed farther away and then migrated inward, though the exact mechanism remains unclear. These stars orbit the black hole at tremendous speeds, providing astronomers with unique laboratories for studying gravity and stellar dynamics in one of the most extreme environments in the galaxy. The Milky Way's magnetic field is revealed by polarized light. While we can't see the galaxy's magnetic field directly, we can detect it through its effects on light. When the starlight passes through interstellar dust grains aligned by magnetic fields, it becomes polarized, meaning the light waves oscillate in a preferred direction. By measuring this polarization across many stars, astronomers can map the orientation and strength of the galactic magnetic field. These studies have revealed that the field follows the spiral arms and is amplified by the galaxy's rotation. The magnetic field plays important roles in supporting molecular clouds against collapse, guiding cosmic rays, and regulating the flow of gas in the galaxy. The Milky Way's disk has a thick component and a thin component. When astronomers study the vertical structure of the galactic disk, they find it's actually composed of two distinct populations. The thin disk, only about 300 light-years thick, contains younger stars, gas and dust, and is where active star formation occurs. The thick disk, extending about 1,000 light-years above and below the plane, contains older, metal-poor stars with more random motions. The thick disk may have formed through early mergers that heated and puffed up the original disk, or from stars that migrated from the inner galaxy. The existence of these two components shows that the disk has a complex history and has been shaped by multiple processes. Triple alpha process creates carbon in stars. Inside red giant stars, where temperatures reach hundreds of millions of degrees, an important nuclear reaction called the triple alpha process takes place. This process fuses three helium nuclei, also called alpha particles, together to form a carbon nucleus. This is how carbon, the element essential for life as we know it, is created in the universe. Without the triple alpha process, the universe would contain almost no carbon or heavier elements. The fact that this process occurs so efficiently is sometimes called the fine-tuning of the universe, since slight changes in nuclear physics would prevent carbon formation. Every carbon atom in your body was created through this process in the core of a long-dead star. The Milky Way's halo contains high-velocity clouds. Among the gas structures in the galactic halo are mysterious objects called high-velocity clouds, large concentrations of hydrogen gas moving at speeds inconsistent with normal galactic rotation. Some of these clouds are falling into the galactic disk, potentially bringing in fresh gas to fuel future star formation. Others appear to be material blown out of the disk by supernovae and stellar winds that has cooled and is now falling back down. Still others may be primordial gas clouds left over from the galaxy's formation, or gas stripped from satellite galaxies. The exact origins of high-velocity clouds remain debated, but they represent an important connection between the disk and the halo. Astroseismology studies stellar interiors by analyzing oscillations. Just as geologists study Earth's interior by analyzing earthquake waves, astronomers can study the interiors of stars by observing their oscillations. Many stars, including our Sun, exhibit periodic variations in brightness caused by sound waves reverberating through their interiors. These oscillations create patterns on the star's surface that can be detected through precise measurements. By analyzing the frequencies of these oscillations, astronomers can determine properties like the star's age, mass, internal structure, and chemical composition. This technique, called astroseismology, has revolutionized our understanding of stellar evolution and has even been used to characterize stars that host exoplanets. The Milky Way may contain primordial black holes. While most black holes form from the death of massive stars, some theories suggest that small black holes could have formed in the early universe from density fluctuations shortly after the Big Bang. These primordial black holes could have masses ranging from microscopic to thousands of times the Sun's mass. If they exist, some could be floating through the Milky Way right now. Primordial black holes are candidates for dark matter, the mysterious, invisible substance that makes up most of the galaxy's mass. Astronomers are searching for these objects through gravitational lensing effects, where a black hole passing in front of a distant star temporarily brightens it by bending and focusing its light. The galaxy's spiral arms are regions of stellar traffic jams. The spiral arms aren't fixed structures rotating with the galaxy. Instead, they're regions of higher density that remain relatively stationary, while stars and gas flow through them like cars passing through a traffic jam on a highway. As material enters a spiral arm, it slows down and compresses, increasing the density. This compression triggers star formation, which is why spiral arms appear bright and blue with young stars. After passing through the arm, stars speed up again and continue their orbits. This elegant explanation, part of density wave theory, helps explain how spiral structure can persist for billions of years without the arms winding up tightly around the galactic center. Some stars pulsate rhythmically, like beating hearts. Many types of stars undergo regular pulsations, expanding and contracting in cycles that can last hours, days, or months. These pulsating variables include Cepheids, RR Lyrae stars, and Mira variables, among others. The pulsations are driven by a mechanism where layers within the star alternately become more and less opaque to radiation, creating a valve-like effect that drives the expansion and contraction. Each type of pulsating variable has characteristic properties that make them useful as distance indicators or as probes of stellar evolution. These stellar heartbeats remind us that stars are dynamic objects, not static points of light, constantly responding to the physical forces within them. As we continue drifting through these cosmic revelations, let your mind rest easy, knowing that the Milky Way holds countless more mysteries still waiting to be discovered. The galaxy spins on through the darkness, patient and eternal, while we float through it on our small blue world, looking up in wonder. The Milky Way's stars follow elliptical orbits rather than perfect circles. While we often imagine stars orbiting the galactic center in neat circular paths, reality is more complex. Stars actually follow elliptical orbits, sometimes swooping closer to the center, and sometimes drifting farther out. Some stars have highly elongated orbits that take them far, above or below the galactic plane, before they swing back down. These orbital variations mean that the neighborhood around any given star is constantly changing. Stars that are neighbors today may be separated by thousands of light years in the future, while new neighbors drift in from different parts of the galaxy. The Sun's own orbit is slightly elliptical, bringing it closer to and farther from the galactic center over the course of its 225 million year journey around the galaxy. Stellar nurseries are hidden within cold molecular clouds. The birthplaces of stars are among the coldest places in the galaxy, giant molecular clouds where temperatures hover just 10 to 20 degrees above absolute zero. These frigid clouds are composed primarily of molecular hydrogen, with traces of carbon monoxide, ammonia, and other molecules. The cold temperature is crucial because it allows gravity to overcome the thermal pressure that would otherwise prevent collapse. Within these clouds, dense cores begin to contract under their own gravity. As they shrink, they heat up, eventually becoming hot enough to ignite nuclear fusion. The Orion Molecular Cloud Complex, located about 1,500 light-years from Earth, is one of the most active star-forming regions visible from our planet, constantly producing new stars hidden behind veils of dust. Magnetars are neutron stars with the strongest magnetic fields in the universe. Among the most extreme objects in the Milky Way are magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These fields are so powerful that they can distort the shapes of atoms and create intense bursts of X-rays and gamma rays. Magnetars occasionally experience starquakes, violent events where the star's crust suddenly shifts, releasing tremendous energy in a fraction of a second. One such outburst in 2004, from a magnetar 50,000 light-years away, was so powerful that it affected Earth's upper atmosphere, despite the enormous distance. These objects demonstrate just how extreme physics can become in the densest regions of matter. Wolf-Rayet stars are massive stars, shedding their outer layers at tremendous rates. Among the most luminous and massive stars in the Milky Way are Wolf-Rayet stars, evolved giants that have already exhausted the hydrogen in their cores and are now burning helium and heavier elements. These stars are so hot and luminous that their powerful stellar winds blow away their outer layers at incredible rates, losing the mass of Earth every 1,000 years or so. The winds can reach speeds of several thousand kilometers per second, stripping the star down to its core. These stars are relatively rare, with only a few hundred known in the Milky Way, but they play an important role in enriching the interstellar medium with heavy elements. Wolf-Rayet stars are near the end of their lives and will soon explode as supernovae. Time 6. The galactic year varies depending on location in the galaxy. We mentioned earlier that the Sun takes about 225 million years to orbit the galactic center, but this orbital period varies dramatically depending on where you are in the galaxy. Stars closer to the center complete their orbits much faster, perhaps in just a few million years, while stars in the outer reaches of the disk take much longer. Some halo stars on highly elliptical orbits might take 1 billion years or more to complete one circuit. This differential rotation means that the galaxy doesn't rotate as a solid body. Instead, different parts move at different speeds, creating a dynamic, flowing structure where stars and gas constantly change positions relative to one another. Stellar streams crisscross the galactic halo like cosmic rivers. The halo of the Milky Way is threaded with stellar streams, long ribbons of stars that mark the orbits of disrupted dwarf galaxies and star clusters. As these smaller objects orbit the Milky Way, its powerful tidal forces stretch them out, pulling stars from their leading and trailing edges until they form a stream that wraps around the galaxy. The most prominent example is the Sagittarius stream, which loops around the Milky Way multiple times like a cosmic scarf. By mapping these streams and studying their properties, astronomers can trace the history of the Milky Way's growth through accretion. Each stream tells a story of a smaller galaxy or cluster that was consumed, its stars now following lonely paths through the halo. The Sun oscillates up and down through the galactic plane. As the Sun orbits the galactic center, it doesn't stay perfectly within the plane of the disk. Instead, it oscillates up and down, crossing through the plane every 30 to 35 million years. The Sun is currently about 50 light-years above the galactic plane and moving upward. In about 15 million years, it will reach its maximum height of about 250 light-years above the plane, before gravity pulls it back down. Some scientists have speculated that these oscillations might correlate with extinction events on Earth, as the Sun passes through regions of different density or encounters for different levels of cosmic radiation, though this remains controversial and unproven. Metallicity is the astronomer's term for all elements heavier than helium. In astronomy, everything heavier than hydrogen and helium is called a metal, even though chemists would strongly disagree with this terminology. When astronomers talk about a star's metallicity, they're referring to the abundance of elements like carbon, oxygen, iron, and all the others that were created in previous generations of stars. High metallicity stars formed from gas that had been enriched by many previous generations of stellar deaths. Low metallicity stars formed early in the galaxy's history, when there had been fewer supernovae to create heavy elements. By measuring a star's metallicity, astronomers can estimate its age and learn about the chemical evolution of the galaxy. The Milky Way's oldest stars reveal its earliest history. Hidden among the stars of the galactic halo and globular clusters are some of the oldest objects in the universe, stars that formed when the Milky Way was just beginning to take shape. These ancient stars have extremely low metallicities, sometimes containing less than 1/10,000th of the heavy elements found in the Sun. Their chemical compositions provide a direct window into the conditions of the early universe, showing us what the galaxy was like before multiple generations of stars had enriched it with heavy elements. Studying these stellar fossils helps astronomers understand how galaxies like ours formed and evolved over cosmic time. Supernova remnants expand for thousands of years after the explosion. When a massive star explodes as a supernova, the story doesn't end with the initial blast. The expanding debris creates a supernova remnant that continues to grow for tens of thousands of years, sweeping up surrounding gas and creating beautiful, intricate structures. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 CE, is still expanding today at several thousand kilometers per second. At the center sits a rapidly spinning neutron star a pulsar that flashes 30 times per second. Supernova remnants are visible across the electromagnetic spectrum, glowing in radio, optical, and X-ray light. They enrich the interstellar medium with heavy elements and trigger the formation of new stars by compressing nearby gas clouds. The galactic fountain recycles gas between the disk and halo. The Milky Way has a natural recycling system called the galactic fountain. Hot gas, heated by supernovae and stellar winds, rises from the disk into the halo, driven by its high temperature and pressure. As this gas rises, it cools and eventually falls back down onto the disk, carrying with it metals and other heavy elements synthesized in stars. This fountain effect helps redistribute material throughout the galaxy and may play a role in regulating star formation. The cycle operates on timescales of tens of millions of years, constantly refreshing the disk with material that has been processed through the halo. Asymptotic giant branch stars are in the late stages of red giant evolution. As sun-like stars near the end of their lives, after they've exhausted helium fusion in their cores, they enter a phase called the asymptotic giant branch, or AGB. During this phase, the star alternates between fusing hydrogen and helium in shells around an inert carbon-oxygen core. The star pulsates, swelling and contracting, and produces powerful stellar winds that blow off its outer layers. AGB stars are among the most luminous stars in the galaxy, despite being relatively low mass. They're also major contributors to the dust and molecular content of the interstellar medium. Eventually, an AGB star will shed so much of its mass that only the hot core remains, surrounded by an expanding planetary nebula. The Milky Way's central bar funnels gas toward the core. The bar-shaped structure at the center of the Milky Way isn't just a curiosity. It plays an active role in the galaxy's evolution. As gas clouds orbit through the galaxy, the bar's gravitational influence can remove angular momentum from the gas, causing it to spiral inward toward the galactic center. This process may feed star formation in the central regions and could potentially deliver material to the supermassive black hole. The bar itself is thought to have formed billions of years ago, possibly triggered by interactions with satellite galaxies or instabilities within the disk. Its presence affects the orbits of stars throughout the inner galaxy. Blue stragglers are mysteriously young-looking stars in old clusters. In ancient globular clusters, where all the stars should be old and fading, astronomers sometimes find stars that appear surprisingly young and blue. These are called blue stragglers, and their existence is puzzling because they seem to violate our understanding of stellar evolution. The current explanation is that blue stragglers are the products of stellar interactions. They may form when two stars merge, creating a single, more massive star that appears younger than its neighbors. Alternatively, they may gain mass by pulling material from a companion star. Blue stragglers remind us that stellar evolution isn't always a solo journey, and that interactions between stars can rejuvenate aging suns. The galaxy's rotation curve reveals the presence of dark matter. One of the most compelling pieces of evidence for dark matter comes from measuring how fast stars and gas orbit at different distances from the galactic center. According to Newton's laws, if most of the galaxy's mass were concentrated in the visible disk and bulge, stars in the outer regions should orbit more slowly, much like how outer planets in our solar system orbit more slowly than inner planets. But observations show that the rotation speed remains roughly constant far from the center, a flat rotation curve. This can only be explained if there's additional, invisible mass extending far beyond the visible galaxy. This dark matter halo provides the extra gravity needed to keep the outer stars moving as fast as they do. Ionized hydrogen regions glow pink in images of the Milky Way. Throughout the galaxy's spiral arms, you can see glowing pink clouds called H2 regions, where hydrogen has been ionized by the intense ultraviolet radiation from hot, young stars. The H2 designation means hydrogen that has lost its electron, becoming electrically charged. When these ions recombine with electrons, they emit light at specific wavelengths, including a characteristic red color. These regions outline the galaxy's spiral arms and mark sites of active star formation. The Orion Nebula is a nearby H2 region visible to the naked eye. These glowing clouds are beautiful demonstrations of how stars transform their environment, illuminating and sculpting the gas around them. The Milky Way contains population 3 star remnants, though we haven't directly observed population 3 stars. The very first generation of stars that formed from pristine hydrogen and helium shortly after the Big Bang, astronomers believe their remnants may still exist in the Milky Way. These first stars would have been massive, hot, and short-lived, exploding as supernovae after just a few million years. Their explosions would have enriched the universe with the first heavy elements, enabling later generations of stars to form. Some of the black holes in the Milky Way may be remnants of population 3 stars, and the chemical signatures of their supernovae may be preserved in the most metal-poor stars we observe today. Finding definitive evidence of population 3 stars remains one of astronomy's holy grails. Emission nebulae and reflection nebulae paint the galaxy with color. Not all glowing gas in the Milky Way is the same. Emission nebulae, like H2 regions, glow because their gas has been ionized by nearby hot stars, emitting their own light. Reflection nebulae, on the other hand, simply reflect the light of nearby stars. Much like fog reflects the light of a car's headlights. Reflection nebulae appear blue because the dust particles scatter blue light more efficiently than red light. Some nebulae, like the famous Trifid Nebula, contain both emission and reflection components, creating stunning combinations of red and blue in astronomical photographs. These nebulae are not just beautiful, they're laboratories where we can study the physical and chemical processes shaping the interstellar medium. The sun's path through the galaxy exposes Earth to varying cosmic ray fluxes. As the sun travels through different regions of the Milky Way, Earth experiences different levels of cosmic radiation. When we pass through one of the spiral arms, where star formation is active and supernovae are more common, cosmic ray exposure might increase. When we're between arms, in the quieter regions, exposure decreases. Some scientists have proposed that these variations could affect Earth's climate by influencing cloud formation, though this remains speculative. The sun's journey also takes us through regions of varying interstellar density, which could affect the heliosphere, the protective bubble of solar wind that shields our solar system from some galactic cosmic rays. The Gould Belt is a ring of young stars and star-forming regions tilted relative to the galactic plane. Our local neighborhood contains a structure called the Gould Belt, a ring of young stars and molecular clouds about 3,000 light-years across, tilted about 20 degrees relative to the galactic plane. This ring includes many of the brightest and most familiar stars in the night sky, as well as nearby star-forming regions like the Orion Molecular Cloud Complex. The Gould Belt is thought to be about 30 million years old, possibly created by a shockwave from a supernova or the passage of a massive gas cloud through the region. The Sun lies near the inner edge of this structure, which helps explain why we see so many bright young stars in our nearby galactic neighborhood. Circumstellar disks are the birthplaces of planetary systems. Around young stars throughout the Milky Way, astronomers observe flattened disks of gas and dust called circumstellar or protoplanetary disks. These disks are the raw material from which planets form. Within the disk, dust grains stick together, gradually building up larger and larger objects, from pebbles to boulders to planetesimals, and eventually planets. Different regions of the disk have different temperatures and compositions, leading to diverse types of planets. Rocky planets form in the hot inner regions, while gas and ice giants form in the colder outer regions. Our own solar system formed from such a disk 4.6 billion years ago, and by studying these disks around other stars, astronomers are learning how common planetary systems are and what processes govern their formation. Variable stars change brightness in predictable patterns. Throughout the Milky Way, many stars don't shine with constant brightness. Variable stars change their luminosity over time, sometimes in regular patterns, sometimes erratically. There are many types of variables. Some, like Cepheids, physically pulsate, expanding and contracting over periods of days to months. Others, like eclipsing binaries, vary because one star periodically passes in front of the other, as seen from Earth. Still others, like cataclysmic variables, undergo sudden outbursts when material falls onto a white dwarf from a companion star. Variable stars have been crucial tools in astronomy, allowing distance measurements and providing insights into stellar structure and evolution. The Milky Way's metallicity gradient shows chemical evolution. As you move from the galactic center outward toward the edge of the disk, the average metallicity of stars decreases. Stars near the center are generally more metal-rich, having formed from gas enriched by many generations of previous stars. Stars in the outer disk are more metal-poor. This metallicity gradient reflects the galaxy's chemical evolution. The central regions have experienced more star formation and more supernova enrichment over time. The gradient also has implications for planetary systems, as metal-rich stars are more likely to host large planets. This pattern of chemical enrichment is common in spiral galaxies and helps astronomers understand how galaxies grow and evolve. As we come to the end of our journey through the Milky Way, let these thoughts settle gently in your mind like stardust drifting through space. You are made of elements, forged in the hearts of ancient stars, living on a world orbiting a quiet yellow sun, halfway out in a spiral arm of a galaxy spinning through the cosmos. Above you right now, if the sky is clear, that same Milky Way stretches across the heavens, a river of light connecting you to the vastness beyond. Every breath you take, every thought you have, is part of the galaxy's long story. Rest now, knowing you are exactly where you belong, a small but meaningful part of an immense and beautiful whole. If you found this journey helpful, please consider subscribing to Cozy Curiosity channel and liking this video. It helps others find their way here for their own peaceful explorations. Sleep well, dream of stars, and may your rest be as deep and peaceful as the spaces between galaxies. Good night.